So, how in the world did we get from AI being this, niche academic thing to the absolute powerhouse it is today? Well, it wasn't just one magic light bulb moment. It was actually a series of huge breakthroughs in three key areas: scale, hardware, and the algorithms themselves. So, let's jump right into this incredible story, kind of following the journey of AI pioneer Jeff Dean to see how these pieces all click together to, well, change everything. And, the whole story really kicks off with this amazing and frankly hilarious dose of humility. We're talking 1990. A young Jeff Dean is working on his senior thesis, and he thinks he can crack parallel training for neural networks with, wait for it, 32 processors. 32. This quote is just perfect because it sets the stage for our entire journey. It's all about the absolutely mind-bending scale that was needed to make AI actually work. Not 32 times more power, but millions, even billions of times more. Right. So let's get one thing straight. The basic idea of neural networks, it's not new. Not at all. We're talking about concepts that have been floating around for over half a century. But for decades, it was kind of like having the blueprints for a massive skyscraper, but you've only got enough bricks to build a doghouse. The theory was solid, but the sheer computational muscle just wasn't there. I mean, just look at that gap on the timeline, from 1990 all the way to 2012. That's more than 20 years of this incredible idea just simmering, waiting. Then, boom, the Google Brain project hits the scene. And they didn't just dip their toes in, they threw thousands of CPUs at the problem. We're talking about training a network that was 50 to 100 times bigger than anything that had come before. This right here was the moment everything changed. This was theory finally smashing into reality. Okay, so how do they actually do it? Well, this is the wild part. They used a technique that, on paper, should have been a complete disaster. It's called asynchronous training. Imagine you have 100 different cooks, all trying to update the same single recipe at the exact same time without talking to each other. It sounds like pure chaos, right? It should have failed. But for some reason, with neural nets, this crazy method, it just worked. And it worked incredibly well, letting them scale up like never before, even if it gave the mathematicians a few sleepless nights. And the results were, well, they were stunning. This wasn't just some neat academic experiment. The model they trained using this wrong method, it delivered a 70% relative improvement on this huge image recognition challenge called ImageNet. 70%. That was the proof. It was this loud, clear, undeniable signal that massive, massive scale was the secret sauce everyone had been looking for. But you know how it goes. Success creates a whole new set of problems. The researchers suddenly had this incredibly powerful new model, but when they did the math, they had a heart-stopping realization. If they actually used it for something like speech recognition, the demand would be so insane they would literally have to double the size of Google's data centers. Just think about that. A software breakthrough had just created a massive hardware crisis. So what do you do? Well, the answer was brilliant. They realized they were using a Swiss Army knife, a general-purpose CPU, for a very, very specific job. So they built a custom tool, the Tensor Processing Unit, or TPU. These things were designed to do one thing and one thing only, the specific kind of math that neural networks need. And here's the clever trick. They did it with less precision, which turns out to be perfectly fine for AI. The payoff was huge. We're talking 15 to 30 times faster and way, way more energy efficient. Problem solved. All right, so the hardware problem is getting sorted out. But the next giant leap forward wasn't just about throwing more power at the problem. It was about a completely new, fundamentally smarter architecture for the models themselves. And this changed the game all over again. This new architecture was all built around a concept called the attention mechanism. Now, think about how older models worked. They'd read a sentence word by word, trying to cram the meaning of everything they'd seen so far into this one constantly changing little ball of memory. It was messy. The transformer, on the other hand, could look at the entire sentence all at once. And when it was trying to figure out the next word, it could pay attention to the most important, most relevant words from anywhere else in the sentence, even if they were way back at the beginning. The paper that introduced this idea had the perfect title, Attention is All You Need. And this chart really tells you everything you need to know about why it was such a big deal. It wasn't just that the results were more accurate. The crazy part is that it got those better results while using 10 to 100 times less compute. Less work for better answers. I mean, that's the holy grail, right? It was a total revolution in efficiency, and it blew the doors wide open for building much, much bigger and smarter models. And this new architecture unlocked something else that was absolutely huge, a new way to train. See, before, you often needed humans to painstakingly label data. But with transformers, you could just unleash a model on the entire internet and have it play a giant game of Mad Libs with itself. Just take a sentence, hide a word, and make the model guess what it is, over and over for trillions of sentences. Suddenly, you didn't need human labelers anymore. The model had a nearly infinite textbook to learn from, all by itself. Okay, so let's recap where we are. We've got massive scale, we've got custom hardware, and we've got this revolutionary new transformer architecture. The models are getting incredibly powerful. But there was another big hurdle. How do you teach them to go beyond just recognizing patterns and actually reason their way through a complicated problem? This led to a discovery that is so simple it's almost funny, but it's also incredibly profound. It's called chain of thought prompting. It turns out, if you just ask a model for the final answer to a tricky math problem, it'll often just guess and get it wrong. But if you ask it to show its work, just like your math teacher used to, and think step by step, its accuracy skyrockets. It's that simple. Just giving the model a chance to think out loud makes it a much better reasoner. All right, another really clever trick is a technique called distillation. The best way to think about it is like a master craftsman training an apprentice. You take your gigantic, super powerful, knows everything teacher model, and you use its wisdom to train up a much smaller, leaner, more efficient student model. And the results you get from this are, well, they're pretty mind-blowing. Just look at this table. If you take a standard model and only train it on 3% of the data, its accuracy is pretty terrible, right? Around 44%. But now, look at the student model. It also only sees that same 3% of the data, but because it's being taught by the giant teacher model, its accuracy jumps to 57%, which is almost the same as the massive model that was trained on all the data. This is the magic trick for packing all that power into a smaller, faster, more useful package. And finally, after all that, the models go through a finishing school of sorts. It's called fine-tuning. This is where they learn how to be genuinely helpful, how to be safe, and how to act in a way that we actually want them to. It's all about feedback. They get rewards for good answers, sometimes from humans who rate their responses, sometimes from other AIs. But the most powerful feedback comes when they do something that's verifiably correct, like writing a piece of code that actually compiles and runs. That's a clear win. So let's put it all together. You take that massive scale, you add the specialized hardware, you build on that revolutionary architecture, and you top it off with these super smart training techniques. What do you get? You get an absolute explosion in what these models can do, leading us right up to the state-of-the-art systems we have today, like Gemini. Now, to really get a feel for how fast things are accelerating, we need to set a baseline. Let's rewind the clock, but not very far. Just back to 2022. Back then, the entire AI community was celebrating a major achievement, a model that could score 15% on middle school math problems. 15%! That was considered the cutting edge just a couple of years ago. Okay, now snap back to today. A version of the Gemini model was tested on problems from the International Mathematical Olympiad. And if you don't know, this is a competition for the absolute brightest high school math whizzes on the planet. And the model solved 5 out of the 6 problems. That's a performance that would earn a human competitor a gold medal. So let that sink in. We went from 15% on middle school math to a gold medal at the World Championships in just 2 years. The pace of progress is just breathtaking. So what does all this crazy power actually mean for you and me? In a nutshell, it's about making expertise accessible to everyone. Think about it. Maybe you have a stack of your grandmother's old recipe cards and you want to turn them into a beautiful website in 2 different languages. A few years ago, you'd need to hire a programmer. Today, you can just describe what you want in plain English, and the AI can generate all the code to make it happen. It's an incredible force for creativity. So what a journey, right? From a thesis about 32 processors to AI models that can reason at a world-class level. The potential here is just staggering. Think about the breakthroughs we could see in science, medicine, and education. But it all leads us to the biggest, most important question of all. As this technology keeps getting better and better at this incredible exponential rate, how do we, all of us, make sure we maximize all these amazing benefits while also being really smart and careful about managing the risks? That's the challenge ahead.